A botanist is running an experiment on two fertilizers that require different amounts of watering. She has 40 test plots, half of which are in sunny locations, half are in the shade. She randomly selects 10 sunny plots and 10 shady plots for which to use one fertilizer with its appropriate watering, while the remaining plots are for the other fertilizer with its appropriate watering. Of the following, which is the most likely, or which is the most important observation about this procedure? So the amount of sun has been accounted for in the design of this experiment. So there's 10 sunny and 10 shady plots for each fertilizer, randomized. So that has been controlled for. What we did not control for with this experiment was the fact that each fertilizer has a different amount of watering that's recommended. So we're using different fertilizers and different watering, which means we don't know which one is going to cause a change in our response variable. So the variables fertilizer and water are confounded. The answer is A. All right. And again, just to make sense of that, if you're using a different amount of water and a different amount of fertilizer and the plants grow differently, what caused it? Was it the fertilizer or the water? Was it both? We don't know.
Wait. I'm just confused how it says how like the water is a confounding variable. It just says like with its appropriate watering. Like I'm just confused with that.
Right. Let's say one calls for, a gallon per square yard or whatever. I'm making something up. And the other one calls for 1.5 gallons per square yard. And so you water appropriately. And then the plants grow differently. Now, was the extra growth in one related to the fact that it had more or less water, like the right amount of water? Or was it related to the fertilizer doing its magic? Fertilizers work by magic, by the way, not by science.
Well, yeah, they come from the wood of forest. So
yeah.
They have from the goji berries.
No, not this again. So there we go. Those are confounded in the sense we can't disentangle what the cause and effect are. Okay, just a second. All right, so we are going to be looking at a little bit of a wrench in the machine as far as means go, which luckily doesn't change things mathematically. Well, it does, but not in a way that we have to. I'm just saying stuff that doesn't matter right now. We're going to look at that, but we're going to start off with this right here, not with this. Though, if you want to get more practice, if you want to go through another hypothesis test with a difference of means, we can do that. So I'm going to leave this here as an option. So if we get to the end of what we're going to do today, and you're like, can we see another example? Certainly we can do that. But anyways, we did look at this yesterday. This is where we left off. So we've got 8 confidence, or not just confidence, 8 I'm saying the wrong thing. 8 inference tests that we can do. And one of them is we have confidence intervals, we have significance tests for different amounts of proportions and means. All right, we're good with that. We talked about it yesterday. So what I want you to do, and this is going to stay up as a as a reference. What I'm going to do is I'm going to show you guys a scenario, and I want you to, on the screen, circle which is the appropriate test to use. And if it's calling for a confidence interval, make sure you circle the confidence interval. So if it's a significance test, pick that. All right. So here's your first one. Read that scenario and decide what the appropriate significance or inference test is. Man, I can't talk. All right. So this is correct. This is 2 sample Z interval. Now, even if you were a little bit lost in the prompt, you might have used the first question as a clue because it says difference in the 2 proportions. Now, I hope you're able to figure it out without using that clue. Because yes, this is 2 different proportions, and when we do the 1 proportion Z interval, they will still give you some kind of a baseline to measure against, but that might say like national statistics say that X% of people do this or that, and that's what you're going to be comparing it against, or that's really with your hypothesis testing, I should say. But just seeing 2 proportions given doesn't necessarily mean it's 2 proportions, because one of them might be a baseline that you're testing against, and the other could be, or in the other case, it could be two sample proportions that you're comparing to each other. All right, hopefully that made sense and I didn't butcher my meaning. Okay. Just a second. Okay, we're good with that. So there you go, a new scenario. Go ahead, circle whatever you think you know the correct test. All right. I would agree. We are dealing with means. Now, you want to look out for a few things to let you know if you're dealing with means or proportions. If it is going to be means, they are going to have to give you the sample size, the sample mean, and the sample statistic. Sorry, the sample mean and the sample standard deviation. So you will have to find that information somewhere, and keep in mind, if it's an AP question, that has to be given to you if you're expected to calculate it, because you're not going to be given a list of data on the AP test and asked to calculate the standard deviation. That's just not something that will happen.
With this table, is y bar the mean of like houses that they scoop into the model?
Yes. So the book likes to use y bar for means, and honestly, you can use any variable that you want, but x bar is what you see with the AP formula sheet and AP a lot more. So that's why we do that. Okay, so that's good. Next one, here you go. There it is. It is a one sample t interval. And just like I mentioned, it has the sample size, the mean, and the standard deviation. So that's going to be your first clue right off the bat. It's going to be means. And so at the very least, you can kind of look at this. And then you can maybe decide, is it one or two means? And you can decide, okay, they're only giving me one set of sample data. So that means it's one sample. And then, deciding if it's confidence interval or a hypothesis test is probably one of the easier things to figure out here. Though there can be situations where it's a little bit trickier. Now, one thing that I haven't talked about and I want to maybe emphasize here, it's a little bit random to do it, but it's worth it. The difference between these two tests and these right here is that this is really the distinction between quantitative data and categorical data. So we're jumping all the way back to the very first test with this. But with categorical data, all you can do is count it. And with counts, you can find out a proportion. How many out of the total fall into this category? And so the proportions will tell you that, and then you can do inference with proportions. Quantitative variables are saying, hey, here are all these actual data values, and we're going to average together to figure out where the average value is. So this is really a fundamental distinction between categorical and quantitative data. So it's worth mentioning here. Maybe I haven't emphasized that enough, but it's worth throwing in just randomly. All right, let's jump to the next one. Okay, so this one caused a little bit of confusion. The answer is this one. It is a one sample Z test. I just say it's not, so therefore it's not. So keep in mind, what we're looking for is how many samples are we looking at? This right here is a kind of a baseline statistic we're comparing against. But if you look, there's only one sample mentioned. It's this L satisfaction sample of 240 students. There's no other sample mentioned here. So there's only one sample to look at. And this will be compared with the null hypothesis to say, we think that the true proportion really is 63%. The alternative hypothesis in this case would be that because they went through this training program, they're going to have a higher acceptance rate. So that is the test being performed. All right.
Your hand sanitizer misfiring got all over my shorts. I clicked it and then it came out after
Well, this is an interesting conversation. Here's your next one. Okay, we have so much consensus going on. It's unreal. Okay. Lots of people thinking this is a one sample t-test, and it is. This is a t-test. We're definitely dealing with means, and the way that we know that, just beyond the shadow of a doubt, is that we see a sample mean, a sample standard deviation, a sample size, and that's going to tell us right off the bat it's going to be means. Okay, there's only one sample given, and we're definitely asked to do a test because it asks for the hypotheses. There we go. See, this isn't so bad. You can figure this stuff out. All right, how many more of these? Well, there's at least one more. Let's figure this one out. So there we go. We've got, this is going to be a one sample Z interval. And remember, the idea behind this is that we're trying to estimate the true percent of, the true percent of broiler chickens infected with salmonella. And if it's really 15%, well, there you go. Make sure you cook that meat until it is heated throughout. Okay. And there it is.
You know what you should do as like a fun activity for stats next year is play bingo.
Oh, there's an idea.
I don't really lay out the framework. Here's a fun idea. If you don't get it right, you get win.
This is going to be a two sample T interval, and we're just getting that confirmed over and over again. But yeah, we can see there are definitely two samples. One is taking route A, another sample from route B, and it asks for confidence interval. You can see the means and the standard deviations, which is telling you it's means. All right, fun times all around. We've answered almost all of these. So how many more? So there it is. Here's the last one. All right.
I'm making a competing YouTube channel to do some businesses on the lectures.
So, okay. So we are looking at two samples in this case, a 2004 sample, a 2006 sample. Now, this could have theoretically been a one sample Z-test if they just told us that in 2004, 33%. If they didn't give us the actual sample and the numbers, and it didn't seem like we were actually comparing these two that way, then this could have been a one sample. But we can see that there is the actual sample, 33% out of 868. It gives us a sample size and the sample proportion. That's all we need to know. And then another sample size and proportion. And this gives us all the information we need to do a two sample Z test. We know that it is a Z test because it's saying, do these results provide convincing evidence that more parents are checking? As opposed to asking in some sort of phrasing that if it was going to be a Z interval, they would say, what is the true, what is the true value of how much more parents are checking? So that would be a Z interval to find out, what are the possible ranges for how much more parents are checking these days, if that makes sense. So anyways, that's all very good. And follow-up question, how much safer do you feel knowing that parents are checking more and more these days? Does that give you a feeling of comfort and safety?
Also, just knowing that like my friends' phones are being checked is like pretty comforting.
That's good.
So that they're not fresh.
So think about this. That means whenever you guys have teens, it's going to be up to like, shoot, let's see, that's 2004, 2006. That's just 2-year span. It's going to be over 100% of you guys checking your kids' phones when they're in high school.
I won't even get my kid a phone.
There you go.
I'll just microchip.
All right. So we need to talk about something else today, and this is what we're going to finish class with. This is a little bit of a nuance here, and we're still dealing with means, but we're dealing with things a little differently. So if we look at this scenario, we've got researchers designed an experiment to study the effects of caffeine, withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, colas, and other substances with caffeine for the duration of the experiment. During one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebo capsules. The order in which the subjects took the caffeine and placebo was randomized. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression at the 0.05 significance level. Okay, and here are the tables of the results. So here is the part that we have to be careful with. Notice that this is the same subject, and we could almost think of it as a before and after. So they had a depression, the score on a depression test. So we'll just say their depression score is given with caffeine, and the depression score is given without caffeine. Now, what is tempting to do, because we've seen results given in a table like this with a previous example, and what might be tempting to do is say, oh, well, this is just averages. So I'm going to take all this and get, that didn't quite go around, I'm going to get an X bar for that, the average right there, and I can plug this into my calculator, get another X bar for that. So maybe X bar 1 and 2. And of course, I'm showing you the wrong thing to do right here. So maybe you get your X bar 1 and 2, and then you get your sample standard deviation for 1 and 2, and then you move forward. But this is not how we want to approach it, okay? And this is what we call paired data. With the previous results, what was it we were looking at? It was heart rates for students after having, it was dealing with caffeine again, so it's kind of appropriate. So they gave us a table of heart rate change based on having caffeine and not. And, you know, I'm not going to fill in the numbers. They're like 3, you know, -1, all these different numbers filled in this table. But these were not the same person with and without caffeine. It was random people. So this number right here actually had nothing to do with that one down below.
Wait, what was the number of hiding?
3 versus -1. So I'm talking about in our previous example that we went through where was it? Yeah, it was 20 students were randomly assigned to drink caffeine or no caffeine. And then they checked their pulse rates. We did that example in class.
Okay.
They gave the results in the form of a table, but the actual order of results didn't matter. So this 3 has no relationship to the -1 below it. This 3 could have been put over here. I could have just moved it right there, and it wouldn't change my results.
So those are just like their individual changes in heart rates. Right?
Yes.
Okay.
Well, technically, it was the change in heart rate.
Yeah.
Okay, I didn't hear that part. Sorry.
Sorry.
So yeah, it was just a random person. So we could think of these as all independent people, and the results from, you know, the top to the bottom had no relationship to each other. Now that's different compared to this table result. Now we're going to come back up to this new one. This is paired data because we have to treat this differently. So we wouldn't just look at it the same way that we do the first set of data. And what we want to do here is recognize that this is one person who had 2 different results given, with caffeine and without caffeine. And so what we want to do is we want to figure out not the difference of means, but instead, and we're just flip it. This is the mean of differences, all right, which is a weird thing. And so the way that we start this off, so actually, before we jump into the math on this, does the distinction between these two make sense? I mean, it is silence right now,
Yeah,
so
yeah, because the pairs.
yeah,
The top one is paired, and those like kind of are together the 2 values.
exactly. Like I couldn't arbitrarily decide, let's just flip the order and just flip those 2 values. In the first set of data we were talking about, we could do that. There's no problem. Because in the end, I was just going to get the entire average of all of the, you know, caffeine or no caffeine values. But here, these two are connected to the specific value below it. So I can't arbitrarily flip these values around. So if you're in a situation like this, the way that we want to do this is actually start off with we want to get the difference between these two. We have to create a new row right here, and I can just subtract, and we can do it placebo from caffeine or caffeine from placebo, depending on if you have a problem working with negative numbers. I'll just do the caffeine minus placebo. So I'll put C minus P to show that it's caffeine minus placebo. And that's going to be negative 11, negative 18, negative 1, negative 4, negative 6, negative 19, negative 6, negative 3. This is exciting watching basic math go on. Negative 1. And here there actually was a positive result. Okay, this man or woman just wasn't very depressed at all in either case. Okay, so the reason for doing this is now, we can treat it at this point as though it's a single sample t-test. All right, and the reason is because this paired data is now being combined into one data point for each person. And so we're essentially saying, is this right here, does this data give us proof that there is a link that caffeine has an effect on depression for caffeine addicted people? So the parameter that we're actually looking for here is going to be the true, it's not a difference of means. Instead, it is the mu of the difference. So it's the average difference that people experience. So true average difference in depression for, caffeine. I guess that says caffeine. Let's go with it. Minus for caffeine minus no caffeine. That's probably not phrased very well, but in the context, I think you understand what I'm trying to say. Maybe I'd wordsmith that a little differently. The statistic that we're going to be working with is the average difference that we got from our sample. So and I'm going to call it X bar sub diff. And I will say this actually from the beginning. It is incredibly unlikely that on the AP test, you will have to go through the process of doing a hypothesis test for a set of paired data. So you can call this a one sample t-test for a mean of differences, or you can call it for a t-test for paired data, which is probably the more common way of talking about it. Highly, highly unlikely this is going to be something you need to run through. In fact, I'd put the odds pretty close to 0%. But it is important to know conceptually what's going on. So the average difference, if we plug this in, we could get this number. Let's just do it. We'll run through this one scenario, and then from here, maybe just hold on to the conceptual things that matter. So I'm going to go ahead and, to save on time, I'm going to be plugging these numbers in lists, and I'm only worried about the difference row. So I don't care about the original depression level and caffeine versus placebo. I'm just going to put in the negative 11, negative 18, and so on. All right. And I got my numbers here And I encourage you guys to do the same thing. But again, really the more important thing is that we understand how this is being approached. All right, so you can double check to make sure you got the same numbers I did. But notice I'm just labeling everything as X bar sub diff, S sub diff, because again, it's a certain number of subjects that are all getting kind of two different treatments to see how they respond to each one. Or sometimes it's a before and after sort of situation. All right. The confidence level here is, well, it's saying confidence level. So we're actually going to be doing a significance level. I know this is probably set up to do a, confidence interval, but we're going to do a hypothesis test instead. Sorry. When I try and write and think at the same time, or write and talk, I can't do either. I was trying to write, think, and talk. That was a bad combination. Okay. So there we are. So anytime it's talking about confidence level, we're actually going to skip over doing a confidence interval for this. We're just going to do a hypothesis test. All right, so the name of this procedure, this is where I mentioned the name a second ago, but it's really, as long as you can kind of describe it and convey what you're trying to get across, then we'd be okay. So this is what we would call a one sample paired, or actually, let me say it this way. I'm forgetting how it's written. It's called a paired sample t-test. All right, so yes, we technically have two samples, but really it's two samples related to one subject. I know I'm repeating myself. So really we're going to treat it as though it's one sample because we're only concerned about the differences. The conditions here really don't change much. We want to check to see if it is normal, if it's random, if it's 10%, and normal. Now, as far as the random and 10%, that's pretty straightforward. Does it ever say the word random in there? It does say there are 11 volunteers, but remember, random also means that the treatments were randomly assigned. And in this case, whether they got the placebo or the caffeine pill was randomly assigned each day. So yes, we can kind of describe that here. I'm not going to do it. Like caffeine pills were randomly assigned each day, or caffeine versus placebo pills. 10%, there are probably more than 100 people with 110 people with caffeine addiction. So this sample represents less than 10% of the population of interest. All right, the normal, notice that we only have 11 subjects, and no matter what, when we're dealing with means, that's not enough, right? But look at what it says here. Does it say it? Maybe I'm thinking of a different problem. I thought I was reading something. Okay, never mind. So we haven't technically met this one. So here's where we would say this does not meet normal conditions, so results might not be accurate. Notice how I wrote all that out right there. Okay, so we did check our conditions. We add a caveat that lets graders know, yes, this person knows what they're doing. All right, let me erase all this. And let's move on to the calculations. Luckily, if this seems like I'm just throwing something out from left field and it's going to be all new, when we get into the calculation, it's going to be a lot more straightforward. So my generic formula is this test statistic equals the stat minus the parameter divided by the standard error. That's our generic formula for any hypothesis test. Of course, I never set up my hypotheses, so I apologize for that. Let's actually create a null hypothesis right here. The null hypothesis would be that the real difference between these two is 0. There is no difference between having caffeine and not having caffeine and how it affects your depression if you're caffeine addicted. The alternative hypothesis is that, well, because the way we subtracted it, our mu sub diff should be, well, what do we think? Less than or greater than 0? Less than 0. So what this is saying, if we put it back into context, is that when you don't have caffeine and you're caffeine addicted, you will experience a greater level of depression. All right. So that's the idea behind this. And I'm going to pause right here to see if there are any questions. Okay. So this next part right here is luckily where it all kind of comes together, and it won't be a new thing to worry about. We are dealing with means. It's going to be a t. But now my stat is x bar sub diff. The parameter is mu sub diff. All right, and S sub diff, that was found from the calculator.
Oh, okay.
When I plugged in the differences, this row right here, yeah. And then that's going to be divided by the standard error of the difference. Oh, I'm sorry, I want to be more specific than that, standard error. That's going to specifically be, because we're dealing essentially with a one sample t-test, it's going to be the sample standard deviation of the difference divided by the square root of the sample size. And the last thing that we need to think about is, what is our sample size here? What do you think?
11.
There it is. There are 11 subjects. It doesn't matter. There's 22 data points. There's 11 subjects. So it's going to be degree of freedom is going to equal 11 minus 1. So there it is, 10. Okay, so now we can kind of go through, and if we plug this in, we're solving for a t-value. We know x bar sub diff is negative 7.364. The hypothesized difference is that there's no difference at all. The sample standard deviation is 6.918 divided by the square root of sample size is 11. So this is just a one sample t-test. The only thing we had to do differently was do some math on the front end to find out the differences between these two. And beyond that, it's still the same thing. So if I, again, remember the whole point of this is that I want you to understand conceptually what's going on and why we're running the test this way. And when I did this, I got negative 3.530. That's what you got? Okay. So with this, we can go through and we can show on the assumption that there is no difference between these two results, then 1, 2, 3. So I was going to go off my screen a little bit, but somewhere over here is my test statistic. And then going off the screen would be where my p-value is. We can already tell it's going to be statistically significant. All right. Second, you saw that z-score or the test statistic, that should tell you this is going to be statistically significant. You probably already felt it was going to be based on all the results we saw up here. They're all negative except for one. So anyways, we can interpret this. If we actually calculate the p-value here, so I'm going to call it, the p-value, we have to calculate that with a t-CDF. We know that we're going to go from a negative infinity, with this distribution up to a negative 3.53 with 10 degrees of freedom. So you can just run that in your calculator real quick. So I got 0.0027. Right. So it started off kind of this extra little wrench in the machine, this nuance, but mathematically, it's actually a lot simpler than having a difference of means. Okay. So there we are. Hopefully you guys agree that it's 0.0027. We can interpret this. And I'm going to erase a bunch of stuff up here now to have some room to write. And I still have these in the presentation. I'll have those formulas again. So because, I'll write this out, the p-value was less than the significance level, so 0.0027 was less than 0.05, we have convincing evidence, or sorry, we reject the null hypothesis. I was jumping into the next sentence. We reject the null hypothesis. There is, I'll write it that way, there is convincing evidence that, and I'm going to go back to that being deprived of caffeine will lead to an increase in depression. And maybe I'll just write deprived, ... That being deprived of caffeine would lead to an increase in depression. So again, look in the prompt to try and find your phrasing for things. Okay. Now, I can't emphasize enough, you will likely never need to do that test the whole way through. Instead, it would just, maybe there'd be questions say, what would be an appropriate test to use? You read the question and you'd say, oh, well, because this data up here is all dealing with a certain number of subjects, because of that, then I would use paired sample t-test. And maybe that's as complicated as you'll ever see it on the AP test. All right, so I don't want to overemphasize this concept. I just want to introduce it and have you understand conceptually what's going on. Are there questions on this right now? Was it falling into place well enough? Okay. So I'm not going to, this is another one we could do, but it's just the same thing as before. We would be subtracting. The main idea is there are 10 different cars in a fleet. They could use regular or premium gas, and they want to figure out if it's worthwhile to switch to premium gas if they get better gas mileage. So for any one vehicle, you're going to get a difference. And so you're going to get -3 right here, -2, -3, and I'm not going to run through. But once you have this is going to be your data set to do your paired sample t-test with. Okay, now we are running low on time, so I'll just jump over to this somewhere. I will. So here it is, your paired samples t interval. There is your generic formula for this, which isn't much different, and this is not on your AP formula sheet, which is going to give you already a clue that it's likely not going to be something you have to calculate. But you can see the only difference between this and your one sample t interval is that we're dealing with mean of differences and a sample standard deviation for your differences as opposed to your other data. Okay, and we just add subdiff to everything. And right here, your degrees of freedom is going to be the number of pairs. So in our first example, there were 11 people. So yeah, 11 minus 1. In the second, there were 10 cars in the fleet. So it would have been 10 cars minus 1. And this is kind of the bigger takeaway. Like, when is it appropriate to use a 2-sample t-test? And when is it appropriate to use a paired samples t-test? And you can see right here, it's either a difference of means or a mean of differences. All right, when is it appropriate to use either one of them? So right here, how many samples do you have? If there's only one sample given, mean of differences would be appropriate. And then there are situations where if it gives you 2, watch out for 2 samples that pair individuals. Can any piece of data in the first be compared to any piece of data in the second? This is where I was talking about, are they independent? If any can be compared to any, then it's going to be a difference of means, your 2-sample test. But if they must stay in pairs, it's going to be the paired samples. And is there any reference to actually pairing the data? If so, that's going to make it really straightforward. Isn't this exciting? All right, and this is kind of what I mentioned before. Just think about if the observations are independent. Could you rearrange the data tables in any way you wanted? You know, at least along the rows. Could you rearrange the values and would it still come out to the same answer? Okay. So, yeah, if you can't directly compare one value from a row of the table to another value in the second row, then it's going to be 2-sample. Okay. So maybe we can finish with this. I want you to decide if this is going to be a 2-sample t-test or a paired t-test. So we're going to get a little bit more practice. Okay, I like this answer. You guys are honing in on exactly what I would say. And one way to think about this, if it helps you to have the visual of the table, think of how you would write out this data. You know, like you'd have diver 1, 2, and 3, or what, it doesn't matter how many, and then the old versus new. And you can't separate this data. So if it took 10 seconds here and 12 seconds here, it has to go together. So paired is the right way to go. Good job on that. It doesn't give you a table, but you can kind of mentally imagine one or actually physically write one out with hypothetical data. All right, even though we're pulling the fish from the same tributary, we're not comparing the same fish to the same fish. So we can just rearrange the data. If you imagine, here's all your fish 1, 2, 3, and 4. It doesn't matter. I'm not comparing this one directly to that fish. I'm just comparing, I could write the data in any order that I care to. So in this case, it'd be a 2-sample test, and that makes it appropriate there. So that's kind of the main takeaway from today. And I'll have a lot more. We can practice with that a little bit tomorrow also, just to remind you of it. You got some homework, things going on. Have a wonderful day, and I will see you guys tomorrow.